We have one last talk for the bootcamp by Thakkar. Is a privacy research engineer at OpenAI. Previously, he was at Google. He's very familiar name and face in the privacy community, worked extensively on DP, lots of fundamental contributions. And he's going to be talking about something that's very important. How do we audit models?
Thanks for the warm introduction. So happy to be here. I'll be talking about how to audit and mitigate memorization in speech models. This is work that I did previously at Google, and I've been at OpenAI for slightly more than a year. So the work is over a year old, but hopefully the concepts and the techniques used might be useful in auditing state-of-the-art and future models. So just to go briefly over where can privacy leakage happen in a machine learning pipeline. You typically have data storage, an algorithm that you use to train a model, and ultimately you release a train checkpoint, either black box or white box access. Leaks can happen at any point in this pipeline. Training data can get leaked, for example, due to unauthorized access. This can come from internal adversaries, external attackers. So there can be various kinds of ways to protect how to store data or how to access data. Leakage can come from algorithms themselves, whether they are distributed or not, and there are different kinds of risks associated with this. For example, gradients can leak a lot of information. There's a line of work in this area. Here's an example of how images can be reconstructed from a training model, from gradients used to train a model. We also had some work on leakage from training speech models, where you can leak what words were used in an utterance that was used to construct a gradient. The identity of a speaker can get leaked. One of the first things we tried was to reconstruct the actual audio sample. I don't know how good you are at reading spectrograms, but if you just look side by side, we can reconstruct essentially a robotic version of what was being said. So there's a lot of information in samples, in sample gradients, and this carries through even if you have a batch of samples, which typically is present in a distributed setup. So it's not just individual gradients, even batch gradients can leak a lot of information. And the last is release neural networks, and there's a ton of work in this area, some of which was in the earlier talk as well. For speech models specifically, we've seen two families of attacks. One is fill-in-the-blank style extraction attacks. So you give a model an utterance which has some gap in between, and the model will tend to complete that gap surprisingly well. And then there are secret sharer attacks, which will be the focus of this talk. So here I'll focus on memorization that we can measure from release neural networks and on one family of attacks. When we talk about speech models, people can mean various things. One common family is text-to-speech. So the input is a text transcript, and the model will give out a speech utterance. Then there's the reverse, which is speech-to-text, also commonly known as ASR, automatic speech recognition. This is probably the most commonly used type of speech model. Input is an audio waveform, and the output is text. Newer models are natively speech-to-speech. So these are usually used in conversations. Given a speech sample, the model will output a speech utterance. Then there's additional types which are used for auxiliary information in speech. So there's speaker recognition, speech-to-speech translation, so given speech, but get a speech out in another language. And then there are foundation speech models. So a lot of families, types of speech models. Today I'll focus on ASR. There are attacks that exist on other models as well. So some background on the secret sharer framework. This was foundational work in 2019. that was used to measure what was called unintended memorization of textual data in language models at the time. And the procedure was as follows. You handcraft some samples, which are called canaries, that you insert in the training data. So you have complete control over the distribution from which you can generate this, over how often they show up in the training data. And then once you train a model on your data set with the canaries, you can measure the performance of the trained checkpoint. You can contrast it with a decently sized holdout set from the distribution that you created. And this distinction can capture how much a model overfits to the specific samples you inserted, how much did it deviate from, for example, memorization versus generalization. The way this work used to measure this was through this metric of exposure, which is essentially when you measure a model's affinity to the canary with respect to a holdout. This is the negative log of the rank of that canary. So how likely is the model preferring performance on the canary with respect to the holdout? And it's scaled by a constant so that exposure is always positive. The gist is higher the exposure, higher the memorization, more concerned you should be for other kinds of leakages as well. So auditing ASR models is challenging. The state-of-the-art method uses thousands of shadow models that you can use to calibrate memorization. As models get larger, compute costs blow up, and this is increasingly infeasible. So it's challenging because just the sheer scale of the models that you need. And another point is we've seen limited success of adaptations of methods that were designed for language models in particular. I'll share an example soon, but essentially, if I insert an audio canary, which is ohms SSN is some random number, the model learns to do that very well, but it also learns this distribution really well. So if I give another name, Raj SSN is some other number, it does that task as well really nicely. And so the distinction is fuzzed out here.
So it's actually close enough performance-wise in those two examples to essentially be trivially different. That's fascinating.
Yes, the power of your method now decreases substantially. And I'll share experiment results soon. So the goal here is the model should perform distinguishability between seen and unseen canaries to capture memorization well, and this holds on both ends. If canaries are too easy, your power will be low. If canaries are too difficult, the power will be low as well. So for experiments, what we did was we picked a 600 million parameter model, used to be big at the time, and then two benchmark data sets. These are audiobook recordings, so people reading audiobooks. One is transcribed, one is untranscribed. For canary creation, borrowing from the language model literature, we chose the transcript to be random words strung together, so there is no underlying meaning in a sentence. And we used a TTS engine to generate audios for these sentences. We wanted to capture how the model picks up on frequently occurring samples as well. So canaries were inserted in various frequencies. And then to capture randomness in the process, there were multiple unique transcripts for each such configuration. In terms of training, what we did was we pre-trained an encoder and then attached a small decoder at the end, fine-tuned it on this canary inserted data set. So there's a short fine-tuning step which sees canaries, otherwise the model is trained as you would typically, and now we want to measure what the final model might have memorized. How we do this is compute exposure use this metric of character error rate. So how often does the model err on inserted canaries versus a holdout set of 20,000 samples. It's a huge sample set, and we want to see if the model performs distinguishably on the canary. So here's the first result that we had. X-axis on the plot is number of occurrences. Prior work has seen increased exposure with increasing occurrences. Y-axis is exposure with the dotted line on the top showing the maximum that we can get with this size of the holdout. And we see some effect of what we might expect. There's slight increase in exposure with 16, like with increasing frequency, but it was surprising to us that with as many as 16 occurrences, the exposure is still pretty low. It's very close to actually the minimum possible. Minimum is 1, this is around 3. Upon deeper investigation, what we found is the model was actually generalizing really well on the holdout. So an example here, the canary with the ground truth and the transcribed text, and the holdout with the same. The model shouldn't have seen any such sample apart from the canaries that were inserted, but it learns to predict such meaningless sentences really well. So if it hadn't seen canaries, the performance on canary and holdout is poor. Once it sees the canaries, the performance is much better, but it's not distinguishable. So here, yeah.
What's the distribution of these canaries? I understood it's like in the IID random words. So it learns to predict IID random words from a large. How is that?
Right. So the input here is the audio sample. The output is the text. So if a model knows how to predict words well, it can technically do this task, but there's usually a language component in such models which will force it to not predict random words arbitrarily. It will try to complete some information, autocorrect some information. And so without seeing canaries, you get actually poor performance. With seeing canaries, you get a boost, but that's also on the holdout. So your power to measure this goes down. If you look at, for example, finer metrics like loss, and if you train thousands of shadow models, you can still distinguish these things, but that's not easy to do. So then we wanted to do this efficiently. What we did was we proposed a different type of canary. Here we played with the speed of the audio, so extremely fast utterances as canaries. So I like to do this test everywhere. I hope the audio works. We'll see. Is it audible? Does anyone wants to? Yeah, so this is what the utterance was trying to say. All models we tried, and most speech models will fail at this task, naturally because they haven't seen such samples ever in their training data. We wanted to see if such canaries might be useful for capturing memorization. The goal, as I said earlier, was to separate learning from memorization. And the crucial part here is the utterance to transcript mapping is very different from typical utterances that the model sees. It was different previously as well. This is even more. So the fast canary setup is very similar to previous. We just configure our TTS engine to generate 4x sped up utterances. This was an example. And just repeat the experiment now using fast canaries. So the fine tuning is done with the usual data set with fast canaries. What do we get? So this is the same plot as before, but with the fast canaries. And what we see is now even at one occurrence, the exposure is much higher, or like measurably higher than what it was previously at 16 occurrences. And then it saturates pretty quickly. Like as soon as 4 occurrences, we start getting limits of exposure, we start getting maximum exposure. So it increases sharply until we reach like 4 to 8 occurrences and then start saturating. Here's an example of now how the model performs on inserted versus holdout. So on the inserted canary, it gets something like 80% correct, 20% character error rate. On the holdout, it just completely fails. And this can be used to showcase that the model is just picking up information from what it exactly saw, rather than trying to generalize over this distribution.
So the intuition that it fails here because it can't use like an actual concept, like just being able to hear the words, no matter whether it's meaningful, to fall back on, right? Is that kind of the intuition?
Exactly. And if this set was large enough, right? Like if we were to insert like millions of such samples, of course it would generalize. But the fact here is like this is a very small subset, and the model still is able to pick up those nuances, but exactly for those samples that were seen.
These are out of distribution for the reason you said. Doesn't that, in some sense, make it sort of the most likely that the model would memorize because the gradients are large? Is that
Exactly.
intentional, or is it like, would it be good to test other things too?
So our understanding of how, there is a relation in between like how models learn and how we can force the models to memorize. The goal is to design methods that are robust to a general family of attacks. This is one way that we know of. There can definitely be other ways you can design other kinds of things that the model might pick up. But so far, this has been like the most robust way. Like cause large gradients, increase frequency, the models will pick up more. Yeah.
Slightly confused by the memorization generalization dichotomy you're trying to paint, because you're trying to understand a learning algorithm trained under a different distribution and using that as a proxy for when the learning algorithm was used in another distribution. And I understand that, okay, perhaps you can come up with an algorithm which is invariant to minor changes in the distribution, but I mean, I don't know if is the real question to understand is the implicit bias of the learning algorithm correct versus not, or
So the goal.
you're interpolating, I'm assuming, on these tasks.
Yes, it's a really nice question. The goal here is to understand what is the inherent risk that a sample might be at if it shows up in training. So through this task of really out of distribution, fast utterance transcription, we try to see what risk might an individual sample pose in terms of leakage. We could definitely sift through the actual training data set, find out some sensitive private information, see how we can extract it easily, but this is a proxy for such a behavior. So if the model is overfitting to this task, which it can pick up from seen samples but doesn't generalize to any unseen sample, that's a reason for concern for the training method, perhaps, that you should have it to be more robust. So how can we make it learn from some significant set of samples without trying to just overfit to the things that it saw?
Yeah, I think I'm confused with this actually measuring robustness, because these different distributions here. It's maybe, but yeah.
It is a proxy. So rather than actually trying to extract private information from a training set, which is not that easy, we are trying to use this as a proxy for the extent of leakage that would happen if a sample were actually a tail sample.
So maybe a quick follow-up would be, if you test it on other distributions where there is valid, but the distribution is valid, like unlike here where you're adding garbage, but it has like a fatter tail, would it behave similarly? Because if these two scenarios are the same, then we know for sure that it's not an implicit regularization issue. But if one is more pronounced than the other, then the model does actually understand, as you said, the linguistic aspect as well, but it's just overfitting on.
Yes, this is a proxy in the sense of, is the model using the information in a sample to try to do the task, or is it trying to just reduce the loss in some manner, just arbitrarily memorizing to give out a good outcome, which is what we are trying to do in the training process.
Yeah, I guess that's the problem is the task. You have changed the task, so it is doing the task.
Yes. Yes, I think there's some agreement that this is a proxy, but I don't know of better ways to capture this as well. Yeah.
But, I mean, when we talk about memorization, I think that's a lot of, it's characterized much the same way, right? If it memorized, in the prediction case, if it memorized a social security number, it's not supposed to memorize those. Say it's it's a different task it's done. It's learned how to predict or produce social security numbers. It ought not to have done that, say. But then we see that, okay, over a distribution of social security numbers, it will predict specifically these canaries and not others. And we think, okay, it didn't learn the task of social security numbers, it just memorized a few. And I don't know if I'm helping, but it's
So the only nuance here is this is an actual task that the model could conceivably hope to learn. So if there is a name to SSN mapping, we don't know of a reasonable function that the model can learn where the name is Thakkar and the result is an actual SSN that is my SSN. Whereas here, this is an actual task that the model could hope to learn, but just due to the presence of samples that we have controlled, we can showcase how much the model is relying on just the memorization aspect. Because if it were actually learning to predict fast words, you would see that effect on the holdout as well. So
by the way, I don't know if you know, your SSNs are, especially for people born in the US, SSNs are to some extent predictable because apparently there's some numbers that cover where you were born
Wow.
and the year, and so your SSN is not completely random.
maybe birthdays. I should have picked a
Okay, just as a
non-learnable function.
But go ahead,
Yes.
sorry.
There's research in finding such predicate. So if you give me a model, I like to find a predicate for which this behavior happens, given the data set, without having to kind of inject it artificially.
There has been some work, and it's on the lines of if you're given a model and you can run one training step on it. Like you can see what the model's gradient is on some sample that you can construct. You can actually construct optimal canaries. So there is some work in that direction, but given a black box checkpoint or just an arbitrary training process, there is, I'm not aware of good ways to go about it. Usually what we run into is there is a sweet spot of hardness for canary construction where you can observe this, and on both extremes of it you lose this behavior. So there is a lot of art in this creation currently, which would be good to have it formalized or a principled approach to it.
the work on finding sort of the ideal canary, so to speak. Wasn't that related to watermarking models?
There is a connection. You can use them for watermarking purposes, but how to do this really effectively so that you get such strong signals is something that, might benefit from additional work. So we had additional results that larger models exhibit more memorization, which shouldn't be surprising by this point. And then how do you audit speech encoders? So encoders are not end-to-end models. They typically learn over unstructured data, but you can do such kind of auditing for encoders as well. So the goal as privacy researchers is to try to mitigate such memorization. And I'll go over one such approach, which we call sensitivity-bounded training. So essentially, it's how can we bound the change that a single sample can have on the training process. It's a necessary condition for differentially private training. So any kind of DP method that you might have seen bounds the sensitivity of the process. Usually, this is achieved by, per example, L2 norm clipping. So essentially, when you take gradients, if they are larger than a pre-specified norm, you clip them down. If they are within that bound, you do nothing. And then you do your training with additional noise. Prior work has observed this. We also saw for speech model that per example clipping mitigates pretty much all the memorization that you can see. If you add formal guarantees on top, you get a lot additional benefits. But for empirical attacks, you basically get everything down to 0. Has been seen in LMs. We see it here as well. The bottom green plot is now the exposure of the canaries. It's the minimum possible, even for 16 insertions. Continuing with the examples that we had, now for both the canaries and the holdout, the model gives out an empty output. So it essentially has learned to ignore anything it cannot understand really well, and we now get the behavior that's similar, but in the other direction. Yeah.
Just to clarify something, the delta from what you're showing empirically here to do something formal would be the addition of noise. Like you're clipping, you're doing half of DP, right? You're clipping without the noise addition, is that right?
Yes.
Okay.
The noise is the missing part. Sampling also is typically done in usual training procedures, so noise is the remaining part.
But you're showing that clipping gets you a lot empirically, right?
For everything you can measure, it gets you there. Additional noise gives you enough formal guarantees.
So the 4x speed audio sample, does it actually have more information where I'm storing it in the computer as a data point, or it has the same information as the 1x speed sample? I'm just trying to understand whether clipping is like allowing you to...
So it doesn't have more information in the information theoretic sense, but it is more surprising for the model. So like as Dan mentioned earlier, the gradients will be much larger.
So when you use whatever way you're using to store it, it's like the same amount of memory. Okay. So it's...
Probably even less because it's sped up, and so, yeah.
I see. So when you're clipping, it's not the case that you're aggressively clipping the speeded up audio sample much more than the non-speeded up one.
So clipping is here on the gradients. So the gradients will be identical in size no matter which sample you use, but it's just that if it is too large in the norm, you clip it down. Like in terms of memory or in terms of information, you can basically, you get the same object essentially.
Yeah, but the smoothness of the function on individual samples could be different across the distribution, and that could affect the gradients, and it could be that if somehow the scale is just much larger for one set of examples, you would aggressively clip them and hence not see this. But in other things which are not speed ups, but other sorts of, like the garbage word thing is not a speed up, you will not see that effect. So that's why, anyways.
Yeah, I'm kind of in a similar vein. I'm curious, did this hold when you went to those other more expensive auditing techniques that you talked about earlier? Like, yeah, did this clipping method work for those?
It does work. You start seeing some differences at like higher frequencies of insertion. So it's basically now the model does respond, but very, very minutely. Because the gradients are now aggressively clipped, so you need a bunch of them for the model to be even to change its behavior somewhat. Yeah.
When you're doing gradient clipping, what sort of what sort of impact on accuracy do you see for like in distribution sampling?
Good question. So speech researchers care about how good the model is. They care about leakage, but they also care about utility. And so here, comparing to the non-private baseline, first exposure drops to the minimum possible, amazing. Word error rate, which is what is used for capturing performance of speech models. Word error rate was roughly similar, I would say. So it's a 2% relative loss in performance. This is, by the way, the difference between state-of-the-art versus the previous one. So speech models improve in 0.1 word error rate. And this is significant, but yeah, let's say it's about the same. A human may not be able to notice that very easily. If you add noise, this gets really affected. So if you add like dp epsilon 2, the error rate is 10, which people tell me was like 10 years ago. So it puts you back really further apart. What was important here for us was the throughput that we were getting. So the way most training frameworks have been designed is to operate over mini batches. They are optimized for that. And so the throughput that we were getting here is half of the non-private baseline. And so if your speech model training takes X days, now it will take 2X days, which may not be absorbable at in many settings. For example, clipping can also add excessive bias to the training, which has been studied in some works. So this was something that we wanted to see if we can alleviate while still getting benefits of memorization mitigation. So one variant or one generalization of per example clipping is called micro batch clipping, where the idea is you clip the average of several gradients. This materializes only micro batch gradients, so the memory footprint is now improved. You don't need to materialize each sample's gradient. As a result, the trade-off is you get weaker empirical privacy because now each sample can take up the effect of a micro batch size. So what we noticed was speech models were large enough that they wouldn't, like we couldn't do complete training on a single core, but they were still small enough to fit into a core with some samples per core. So there was this special case of per core clipping that was possible here, where we clip all the where we clip the average of all gradients on a single core. And when you have data sharded training, this basically has no memory overhead. Each core will anyways contribute its average gradient to the orchestrator. And there is no compute overhead because, or almost no compute overhead, because this is just a scaling operation on what you would have ultimately given anyway. So what you get with per core clipping, so the red line on the bottom is what we get with per core clipping. Here it was 4 samples per core. We also had experiments with 8 samples per core. And what we saw is memorization is pretty much very close to per example clipping. We lose all the power here that we can measure. The question is, how bad is it in terms of utility and speed? We actually get some improved utility in terms of word error rate. This we studied in another work as well on various production grade models, and this behavior was repeated. So it was a rare win-win for both reducing memorization and increasing performance. And not surprisingly, now the throughput is back to where we were. So we get a good sweet spot where the memorization reduces drastically, exposure drops from 13.5 to 2, and the other 2 metrics are either improved or unchanged.
So isn't that like a year-over-year state-of-the-art improvement, like you were saying earlier?
Yes.
Nice.
So it is an improvement, though by the time this came up, the state of the art had improved a lot. So, but this was still surprising and pleasantly surprising. This result reduced a lot of the friction of adding such techniques in the pipeline, because it's very easy to add, throughput doesn't suffer, you get benefits of utility, you get benefits of mitigating memorization. So, yeah.
Did you measure the non-private baseline without canaries? The canaries were your non-private.
What do you mean?
That non-private baseline is the measurement where you've included the canaries in the non-private training, right?
For the utility?
For utility.
It's without the canaries.
Oh, that's utility without canaries.
Yes, exactly. So utility essentially doesn't change here. Like maybe in the second decimal place you'll get some deviation. Canaries were less than 0.01% of the whole data set. So, yeah.
So I have a question. So here you are doing per example clipping, and maybe this is an infrastructure issue. So, there was a point when we tried to do something similar, but my understanding is that doing per example clipping in things like PyTorch is very hard, because either you have to re-engineer the thing, or your speed slows down drastically. So how did you get around that?
For this,
Yeah.
we actually paid the cost.
Oh, you pay the
So this was the critical point here. It doesn't seem like a difficult operation to add, but the way our frameworks have been optimized, it turns out to be. And now training is even more distributed, even like probably across data centers. So per example clipping does add significant cost.
Sorry, where do you draw the line? I mean, 2 is green. Is 3 green for exposure? Like, where do we draw the line to go from green to red? And I noticed the confidence intervals are also like pretty wide. So like, should we factor in the fact that there's variance in those quantities, and what should we do with that?
Awesome question. I would consider it similar to what is a good epsilon. Right? For some applications, 2 might be concerning. For many, it might be. But essentially, I think how you want to capture it, or how I try to capture is it, if it occurs 16 times in the data set, do you consider it a secret? And if the model somewhat prefers it to a holdout of 20,000 samples, how motivated would an adversary have to be to get information from this versus other sources? So how motivated the adversary has to be, how hard they have to work, and what do they ultimately get? If they get a slight increase in their confidence of what the prior they had and what they get after using the model, that may not be that concerning in many cases. If it's a very sensitive application, that really, then per example clipping might be the way to go. Yeah. Yeah, Edwin.
Yeah, I wanted to add, so you used HGD all along, and the only clipping was kind of intervention, but have you looked into like stability-aware training, or this sort of like alternative ways of training that make for better generalization? Does this? I suspect this would work, but I wonder whether.
So we actually here didn't touch the training method.
Yeah.
So we wanted to capture what people were using to train the models in their existing pipeline, which included adaptive optimizers, which included a lot of other bells and whistles. And we wanted to try to see first how much at risk it is for memorizing data, and then how can we mitigate that. So this is like actually not vanilla SGD plus clipping. It's actually like a lot of other things that go on top for optimizing performance, for optimizing utility, and this is on that. It's treated as a black box actually. So we don't want to.
What I'm trying to say is that this seems to be an outcome of that generalization, and maybe there's other approaches that are aimed at doing better generalization, and as a side effect, you would sort of kill this behavior because you just, by design, you're going to ignore everything up to 16 examples or whatever.
Absolutely, absolutely. And you want to try to get here because if you analyze something on a specific learning method and somebody changes something, you then wouldn't want to repeat all your experiments again, analysis again.
Sort of back to his point, if you do use SGD for this is performing the task, is memorizing the tail, is generalizing everything about the
So
tail.
you actually don't want to ignore 16 examples. You want to only ignore 16 examples that don't follow, let's say, the grammar. If there are 16 examples that follow grammar but are rare.
Distribution could be bimodal. I mean,
Yeah,
that's
yeah,
unclear
exactly,
what
yeah.
that means. Like, yeah.
But the canaries are out of distribution.
Yeah.
One thing you said is that you've also noticed that clipping, whether per example or per core, helps with transformers or language models. Is that documented? Because we have experiments where clipping alone was not sufficient.
So maybe the question here would be how aggressive is the clipping? Mm-hmm. And usually here what we've treated and even prior work has treated is if you're going for mitigating memorization, you might as well go the max you can, which is clip everything to the minimum of the gradient norm or to something that squishes all gradients. So each sample is now treated equally for your learning process. If you set, which is not the case when we try to apply DP, because you want to balance learning versus bias, and there might be a sweet spot if you are going for a DP style approach. So this is where we actually ensure this 2.5 clip bound clips all the samples. Awesome. So in the remaining few minutes, I'll just cover what I'm interested in, what might be useful to understand. So one, future direction. is models are now multimodal increasingly. They are getting larger by the day. Here's a plot after which companies stop reporting sizes even. And so a lot of work has been on larger models, have been shown to memorize more. And multimodal user data is increasingly used for training. So there is a dire need for attacks and methods that can focus on this. All methods we know of focus on example level leakage. There is some recent work on user level inference. I think Peter has been involved in some of those. The goal here would be to design user level privacy leakage attacks for multimodal models. And there is some recent work last year on cross-modal memorization in vision language models. You can add speech into it, video into it, and you can get increased attack surfaces. It would be nice to understand how much leverage can an adversary have if a user has multimodal data. And even negative answers here would be useful because they might indicate something about how our models learn. They might treat each modality differently, and we might benefit from that as well.
Sorry, I was going to say that we have also some work from 2024 on cross-modal memorization.
I should definitely look at that. Another direction is moving privacy upstream in model training. So not surprisingly, training pipelines are getting more complex. There are various stages of training now, and methods evolve rapidly. So you often find one component of training gets replaced by another, and so very rapidly evolving. The nice thing is data practitioners already know how to use data. So if you give them a bunch of samples, they'll know how to put them in the pipeline. And even from formal privacy notions like DP, we know that privacy upstream can benefit downstream use cases. So if you take care early on, downstream use cases can benefit those as well. So the goal here is to design privacy methods that integrate at the earliest stages of training. Ideally, it should be as native as some sort of pre-processing or data augmentation that practitioners already do. And one really nice example is private synthetic data or some sort of private rewriting that frontier models could be capable of doing. A nice example here is a recent tutorial at ICML, DP-fying, how to DP-fy your data. So yeah, lots of useful stuff there. So with that, I'd like to conclude. Thank you very much.
All right, let's try to break for 15 minutes and come back for the panel so we can continue this discussion during the break. Thanks.
A quick question, actually. I'd like to draw a diagram.
Yeah, okay.